Good morning. Let's start assignment 5. Example 1. Prove that z-axis is a subspace of R3, that is the 3-dimension in reals, and also find a basis for the z-axis. Now let W be the z-axis because it is given to us that z-axis, we have to prove that this z-axis is a subspace of R3. So let me consider this z-axis to be W, and I have to prove that this W is a subspace of R3. And for subspace, 3 things needed to be proved. First, W should be non-empty, and then it is a subset of R3, and last, if we take any two elements from this W, then their linear combination also belongs to the W. If these 3 conditions satisfied, then we say that W is a subspace for R3. So let's start. Alright, now our W is the z-axis. So what kind of element be present in W? Having only the z element, so it is 0, 0, z, right? And where z is belonging to real numbers. So z-axis, only the z-axis is there, and the coordinate of x and y is 0, 0 here. Now to prove that W is a subspace, number 1 is, now since I'm already having the element in this W, so W is naturally non-empty. So since 0, 0, 0 belongs to W. Now here Z is taken to be 0, and because 0 is real number, it is given that you have to take that Z such that Z belongs to the real numbers, and I know that 0 is also a real number. So I can take the element like this 0, 0, 0, which belongs to W. Yes, it is belonging to W. So therefore W is non-empty. And clearly W is a subset of R3, of course. Let me take 2 elements from W and let U and V be the 2 elements from W, and I'm taking U to be as 0, 0, x1, and this is, sorry, I have to write Z1, and then V to be taken as 0, 0, z2, right? And let me take my scalar to be alpha, which is belonging to the real numbers. Then this z1 and this z2, they are also belonging to the real numbers. So z1 and z2 also belongs to the real number according to the definition of W. Now since alpha u plus v is equal to alpha, write the value of u here, plus v is 0, 0, z2. Let me add these two. I get alpha times 0 is 0 plus 0. Then alpha times 0 is 0 plus 0. And alpha times z1 plus this z2. And because z1 and z2 already belonging to R, and alpha is also belonging to R, which means this linear combination alpha z1 plus z2 is also belonging to R. And whenever this third coordinate named as alpha z1 plus z2 belongs to R, and I'm already having 0 in the first coordinate, and second also there is 0, and third value is belonging to R, which means this complete element is belonging to W according to the definition of W. 0, 0, Z should be such that that whole complete Z should belongs to real numbers, and we have proved that 0, 0 is already there, and this complete alpha Z1 plus Z2 is belonging to R, right? Which means this alpha U plus V is belonging to W. So alpha U plus V is belonging to W. Thus, W is a subspace of R3, right? Now I have to find out the basis for z-axis. So for that, I need to take one element from W first. So let me take 0, 0, z from this W. Then this 0, 0, z can be written as, I need to have the linear combination for this, right? So this can be written as z 0, 0, 1. Yes? Can I write like this? Alright. Which means 0, 0, z is a linear combination of 0, 0, 1. Right? But 0, 0, z was arbitrary. So every element of W is a linear combination of this 0, 0, 1. Thus, W is generated by only 0, 0, 1. Right? Now to check this 0, 0, 1 is linearly independent or not, for that I have to take one scalar and multiply the scalar with this. This is equal to 0. Now since zero, 0, 1 is not equal to 0, 0, 0, right? This is your non-zero, which means what? Alpha is 0, which means our scalar is 0, which means in this linear combination there is only one scalar and that is 0, and this is non-zero, which means scalar is 0, which means it is already linearly independent. So therefore alpha is equal to 0. This implies alpha is 0, but this is non-zero, which implies alpha is 0. Hence, this is linearly independent. So a vector to be linear independent, for that alpha, all the scalars should be 0 in that linear combination. Now since 0, 0, 1 is linearly independent and W is generated by this 0, 0, 1, so from these two conditions 0, 0, 1 is a basis for W, right? When the vector is a basis for W, if it is a generator of the subspace and it is linearly independent, and both these things are proved here. Alright? Okay. Next example. Let V be the vector space of all ordered pairs of complex numbers over the field R. Find a basis for V. Now here it is given that the vector space V is of all ordered pairs of complex numbers. Right? I have to find the basis for V. So by hypothesis, V is equal to, now what kind of element is present in V? Because it is having the ordered pair of complex numbers. So A plus iota B, C plus iota D. Such kind of element is there, where this A, B, C, D belonging to reals. Right? And you all know that for a complex number, A is the real part and B is the imaginary part. Right? Iota B, this is your imaginary part. Okay. Now let A plus iota B as C plus iota D. This is equal to, how can I write this as? Can I write it as A comma C plus iota B comma iota D? Can I write like this? Yes, of course. If you add these two, you will get back your A plus iota B comma C plus iota D. Now again, can I write AC as A comma 0 plus 0 comma C? Can I write like this? If you add these two, you will get back your AC. Similarly, can I write iota B iota D as iota B comma 0 plus 0 comma iota D? Yes, of course I can write. Okay, now take this A outside. This is A10 plus this is C01 plus this is B iota 0 and this is D0 iota. So this is nothing but the linear combinations of 1 0 0 1 iota 0 0 iota, right? So A plus iota B, C plus iota D can be written as the linear combinations of these, right? So this is the linear combinations of these, all these 1 0 0 1 iota 0 0 iota, but this is arbitrary. right? Which means every element of V can be written as a linear combinations of all these. Yes, which means V is generated by all these vectors. Now I have to prove that these are linearly independent. So secondly, let me take my scalars to be alpha, beta, gamma, delta for each of them. Sorry, for respectively. Okay, so alpha for taken to be for 1 0, and beta is for 0 1, gamma is for iota 0, and delta is for 0 iota, and this is equal to 0 0, right? Okay, let me multiply this now. This is alpha plus beta. Okay, so this is alpha comma beta plus iota wait, iota gamma, iota delta. Yes, if you add these you will get this. Okay, so this is equal to 0 comma 0. Okay, again adding this, alpha plus iota gamma, and I get beta plus iota delta. This is equal to 0 comma 0, which means alpha plus iota gamma is 0 and beta plus iota delta is 0. Now equating the real and imaginary part, because 0 can also be written as 0 plus iota 0. Can I write like this? Okay. Here also you can write like this. That doesn't matter. Now equating the real and imaginary part, you get alpha to be 0, then beta is 0, then gamma. Equate this imaginary part, you get gamma also be as 0. And then delta is also 0, which means the scalars I have taken as alpha, beta, gamma, delta, all these scalars are 0 0 0 0, which means all these vectors are linearly independent, right? So these are linearly independent and V is also generated by them. So from 1 and 2, this is a basis for V, right? Okay, thank you so much for watching this video. We meet in the new video. Thank you. God bless.